Okay, we're going to move on from integrals for just a bit and talk about indeterminate forms of limits. And you'll think that maybe you talked about this last year, which you did some, but we're going to delve into this a little more deeply and then put it together with other stuff. So, you know that indeterminate forms are either, well, generally you learned last year that they were 0 over 0, but they can also be infinity over infinity. But not all indeterminate forms can be evaluated doing algebraic manipulations. And you learned how to use L'Hopital's rule to make the algebra easier. But we're going to use algebraic and transcendental functions. So transcendental functions are simply functions that do not have a polynomial form. So, like rational functions have a polynomial form, but transcendental functions do not. So we're talking about sine, or natural log, or e. Okay, well we know that L'Hopital's rule says that if I get 0 over 0, or infinity over infinity, that I'm allowed to take the derivative of the top and the derivative of the bottom, and then evaluate the limit again. Okay, you learned that last year. And you learned it for problems like number 1. So that you wouldn't have to rationalize the numerator and the algebra gets ugly. Okay, but if I plug in 0, I get 1 minus 1 minus 0, so that's 0 on top, and on the bottom I get 0. So I'm allowed to use L'Hopital's rule in that case. So if I do the derivative of the top, I will get 1 over 2 square root of 1 plus x. The minus 1 goes away, and the x goes away, so at minus 1/2 over 2x. Now, I have not evaluated the limit, so I need a limit in front of it. Now, if I plug in 0 this time, I get 1/2 minus 1/2 over 0, which again is 0 over 0, so I can do L'Hopital's rule. This stuff at the top is actually your reasoning as to why you can use L'Hopital's rule, and you need to write it down. So I need to do the derivative again. So remember that this first term is really 1/2 times 1 plus x to the negative 1/2. So the derivative of that would be negative 1/4, and I have square root of 1 plus x cubed, and the derivative of 1/2 is 0, and on the bottom I would have 2. Now when I plug 0 in, so I don't need a limit in front anymore, I have the square root of 1, cubed is 1, so I have negative 1/4 over 2, and so that would be negative 1/8 for my limit. Okay? So you learned L'Hopital's rule in those instances last year for saving you your algebraic manipulations. But in BC calculus, we do more advanced functions with it. So if I have e to the 2x minus 1 over x, and I plug 0 in for x, I will get 1 minus 1 over 0, or 0 over 0. So I can do L'Hopital's rule. So the limit as x approaches 0. The derivative of e to the 2x would be 2 e to the 2x. 1 would go away, and the derivative of x is 1. So now when I evaluate by putting in 0, anything to the 0 power is 1, times 2 is 2, over 1, so my limit is 2. What if we have a natural log, and this time we're approaching infinity? So when I plug in the natural log of infinity, I will get infinity, and as x goes to infinity, I'll get infinity. Well, that is also a form in which you can do L'Hopital's rule. So I can say that's the limit as x approaches infinity. The derivative of natural log of x is 1 over x. The derivative of x is 1. So 1 over infinity is actually 0, and that's what will be the answer to our limit. Now you could also use your rules from pre-calculus because while the top is infinity, the bottom's infinity faster, so the bottom's going to dominate. So you could say like that infinity is bigger. And so when you take a number and divide by infinity, you're going to get 0. So either way, I think probably by using L'Hopital's rule is just as easy in this particular case. Okay, so these are just some more examples. In this particular problem, so when I plug in negative infinity and I square it, I'll get positive infinity. So this will be positive infinity over e to the negative. Negative infinity will be e to the positive infinity, which is infinity. So I can do L'Hopital's rule. So this will be the limit as x approaches negative infinity of 2x over negative e to the negative x. That's not really going to help me because I still have an x on top, so I'm still going to get infinities, right? This time I'm going to get negative infinity over negative infinity because of the negative here. But I can do L'Hopital's rule again. So I'll get 2 over positive e to the negative x. So I have 2 over positive infinity, which would be 0. So our limit there is 0. Okay, trig function 1. So if I plug in 0, the sign of 0 is 0, and x is 0, so I can straight off use L'Hopital's rule there. So I do the limit as x approaches 0, and the derivative of sine is cosine 5x times the derivative of 5x, which would be 5, and the derivative of x is 1. So the cosine of 5 times 0 is 0, cosine of 0 is 1, times 5 is 5, would be our limit. All right. How about the cube root of x minus 1 over x minus 1? So we know if we plug in 1, we get 0 over 0. So I can use L'Hopital's rule. So the limit as x approaches 1. When I do the derivative of the cube root of x, that'll be x to the 1/3. So it'll be 1/3 x to the negative 2/3. So times the cube root of x squared over just 1. And when I plug in 1 now, you'll see I just get 1/3. Okay. And then for 7, if I plug in 2, I get 0 over 0. And so I can do L'Hopital's rule. The limit as x approaches 2, 2x minus 4 over 3x squared minus 12. But when I plug 2 in again, I still get 0 over 0. So I have to do L'Hopital's rule again. And I will end up with, take the derivative, so that's 2 over 6x. Now plug in 2, I get 2 over 12, or 1/6 for my limit. Okay. Now, notice that these two limits here are as x approaches numbers. Okay. In number 8, though, notice that x approaches infinity as well as in number 9. When x approaches infinity, you're really looking for your horizontal asymptote. And I don't know if you remember, but in pre-calculus you learned some rules where if the degree in the denominator and the degree in the numerator, so if the numerator is equal to the denominator, then it's leading coefficient over leading coefficient. And if the numerator is smaller than the denominator, it's 0. So I would argue that this problem is, because you have to do the derivative so many times, because you have a fifth power, top and bottom, this problem is actually more easily done using the pre-calculus rules. So this limit's really just negative 4/3, because the degrees are the same. So it'd be leading coefficient over leading coefficient, which is your horizontal asymptote. In 9, it's actually the same case, because when you do the square root of x squared, you get x. So the powers are really the same. So you would get leading coefficient over leading coefficient for your limit, so it'd be square root of 5 over 8. We can graph that, and I can show you if you're not convinced of that. So there are other indeterminate forms that we really don't talk about as much, and they are 0 times infinity. Like, which one dominates? Is it the 0 or the infinity? 1 to the infinity. We know 1 to any power is 1, but does that happen when it's infinity? Infinity to the 0. Anything to the 0 power is 1. But what if that's infinity? 0 to the 0. We know anything to the 0 power is 1, but what if the base is 0? And infinity minus infinity. Well, that should be 0 because infinities match, but is that really the case? Is one infinity bigger than the other? So when we see these indeterminate forms, which there are 5 of them, we can use algebra to make them into those forms, 0 over 0 or infinity over infinity. Then we can use L'Hopital's rule to evaluate them. Now, I'm just going to do a quick example of why these are still indeterminate forms. These 5 forms are indeterminate by using this example of 0 times infinity. This will be a stretch for some of you to actually believe this, but here we go. Okay, so if I just do what limits tell me to do, and I plug in 0, I'd have 0 times 1 over 0, and we know 1 over 0 is really infinity. And so this would be 0 times infinity, right? If I just think about it. Algebraically, if I do this, I'd have the limit as x approaches 0 of x over x, which is really just 1, which means the answer is 1. So in this particular case, I started with 0 times infinity, and my answer was 1. Okay, next example. Well, I plug in 0, so I get 0 times infinity again. But this time when I do the algebra, I get 2 for my answer. So here's an example where infinity times 0 is 2. All right, another one. Plug in infinity. I get infinity times 1 over infinity, which is 0. But if I look at algebraically, I'd have x over e to the x. So I could plug in infinity, and I could do L'Hopital's rule. And that would be equal to the limit as x approaches infinity of 1 over e to the x. So I get 1 over infinity, which is 0. So this time, infinity times 0 is 0. So you can see the dilemma here. I'm getting a different answer each time. That's why we say that they're indeterminate. We don't know what kind of an answer we're going to get. So we want to try to get any of these 5 indeterminate forms to change them into either 0 over 0 or infinity over infinity, so that I can use L'Hopital's rule to then evaluate them. All right, so the first one. If I plug in infinity, I get infinity times the sine of, really 1 over infinity is the sine of 0, which is 0. Well, that means that I can rewrite this. So I can rewrite this by doing some algebraic manipulations. I can say that's the sine of 1 over x divided by 1 over x. Well, if I divide by 1 over x, it's the same as multiplying by x, right? Why is that helpful? Well, because now when I plug in infinity, the sine of 1 over infinity is 0, the sine of 0 is 0, 1 over infinity is 0. So now I can use L'Hopital's rule to evaluate this problem. So that would be the limit as x approaches infinity. Take the derivative of sine, be the cosine of the same angle, times the derivative of the angle, so negative 1 over x squared, over the derivative of the bottom, negative 1 over x squared. Those cancel. Now when I plug in infinity, I really have the cosine of 0, which is 1. So by rewriting this limit, I'm able to evaluate it when before I couldn't, because it was in a form that I just didn't recognize. 3 more examples. Okay? Plug in 0. 1 over 0 we say is infinity. 1 over 0 is infinity. Infinity minus infinity is one of those 5 forms. So how can I rewrite something that's a fraction, that's a difference of fractions, to maybe be 0 over 0 or infinity over infinity? Hopefully you say get a common denominator. And my common denominator would be x times sine x, which means my first term is going to be x over sine x. My second term is going to be sine x over x. So, now when I plug in 0, I have 0 minus 0 over 0. I can do L'Hopital's rule. So I get the limit as x approaches 0 of 1 minus cosine x over, but I do have to do product rule here, unfortunately. So I have to use the product rule because I have x times sine x. So the derivative of x is 1 times sine x plus x times the derivative of sine x would be cosine x. So now when I plug in 0, I have 1 minus 1 over 0 plus 0. So that's 0 over 0. Then I have to do L'Hopital's rule again. So I have the limit as x approaches 0, derivative 1, 0, derivative cosine sine, negative sine, but since it's already negative, it would just be sine x over. Derivative of sine is cosine, and I have to use the product rule here. So plus 1 cosine x plus x, derivative of cosine is negative sine, so minus sine x. Alright, so plug in 0. I get 0, and on the bottom I get cosine of 0, which is 1, plus cosine of 0, which is 1, plus 0. So I get 0 over 2, so my answer is 0. A lot of work to get an answer of 0, I know, but that's how it turns out. Okay, 12. If I plug in infinity, I get e to the negative infinity. Well, that's really 0, and the square root of infinity, which is infinity. So how can I rewrite that? Well, when I have a negative exponent, it's easy, because negative exponents can be written in the opposite place with a positive exponent. Now when I plug in infinity, I get infinity over infinity, which allows me to do L'Hopital's rule. So I'll have the limit as x approaches infinity of 1 over 2 square root of x over e to the x. So when I plug in 0, I get 1 over 0, which is infinity, over infinity again. Or, well, it helps if you actually write what you were asked. It's x approaches infinity. So I get 1 over infinity, which is 0, over infinity, which is 0. Okay? I promise not all the answers are 0. All right, last example. Again, I have a fraction. If I plug in 1, I get 0 minus 1 over 0. I'm sorry. 1 minus 1 over the natural log of 1 is 1 over 0, which is infinity. Minus 1 over 1 minus 1 is 0, so that's infinity. So I have infinity minus infinity. Well, if I get a common denominator, I will get the natural log of x times x minus 1. So I have to multiply the first fraction times x minus 1, and the second fraction times the natural log of x. Now when I plug in 1, I get 0 over 0, and I can do L'Hopital's rule. So that'd be the limit as x approaches 1 of, the derivative of x is 1, derivative of negative 1, 0. Derivative of natural log is 1 over x, but there's a minus sign there. And then on the bottom, I have to again use the product rule because I have two things multiplied together. So that'd be 1 over x times x minus 1 plus the natural log of x times 1. So if I plug in 1 now, I get 0 on top and 0 on the bottom. So let's do L'Hopital's rule again. So that's the limit as x approaches 1. So the 1 goes away, so that would be positive 1 over x squared over our product rule, positive 1 over x squared times x minus 1, plus 1 over x times 1, plus 1 over x. So now I plug in 1. So on the top, I will get 1. On the bottom, the first term will be 0, but this next term will be 1, and the next term will be 1. So 1 over 1 plus 1 is 1/2 for my limit. Okay, so we will practice indeterminate limits in class tomorrow, and hopefully this will clear some of these things up for you, and you can ask questions if you have questions.